Question number 9. Two identical spheres are released from a magical device at time t equals 0 from the same height h as shown above. Sphere A has no initial velocity and falls straight down. So, there's sphere A that we're considering. Sphere B, on the other hand, is given an initial horizontal velocity of magnitude, initial velocity at time 0, and travels a horizontal distance d before it reaches the ground. Again, the word horizontal appears there. The spheres reach the ground at the same time. You should already know that for a specific reason, even though sphere B has more distance to cover before landing. In the magical worlds we all like, air resistance is negligible. That means these are objects in free fall, right? Even before we began talking about forces, we defined free fall as when objects are falling under the sole influence of gravity. You know that means that the only force acting on these two objects is the force of gravity. We learned about that in the context of kinematics, that is, they experience the same acceleration because they're in a local gravitational field and the Earth is so ridiculously huge that it does not matter what the mass of these two little objects are, they experience the same acceleration. So, the dots below represent spheres A and B. Draw a free body diagram showing and labeling the forces, not the components, exerted on each sphere at time final, divided by 1, 2. In other words, halfway through time. Basically, they're trying to ask you to think about, we're not talking about when it's right at the top, we're thinking about halfway down to the ground, how much time it takes. You already know because the problem tells you they hit the ground at the same time, which means they must be experiencing the same vertical acceleration. So we are considering them at the same height, at the same time. We're in the middle of the air, not on the ground and not on the launching device that's up above. So if they're experiencing only the acceleration due to gravity, they're in free fall, and their masses are the same because they're identical, then their free body diagram should be the same. They're only experiencing the force of gravity acting downward. No other forces are acting on these devices. So part B, in a clear, coherent paragraph-length response, explain why the spheres reach the ground at the same time, even though they travel different distances. Include references to our answer in part B. So there's a couple things, and I'm going to sort of list stuff over here as well so that I just have some room. There's a couple factors that are important to consider in your paragraph length response. One is thinking about what that word identical means. So that gives us some clues. These are objects with the same mass. You can reference, if you want to, what I said about that they're in the same gravitational field, which we haven't talked about what a field really is yet. We'll get there in a little while. I know I say that all the time and it drives you all crazy. Okay? You know that these are objects in free fall. So you can define what free fall means, which is objects under the sole influence of gravity. Ooh, influence. I can spell really well. That sole influence of gravity is important, and that's what that neglect air resistance tells us. That's how we can figure that out. And so they fall with the same acceleration, that's something given in the problem. So those are important pieces that we're factoring into our assumption. And that part of what you know about what free fall means is that they experience the same acceleration. They have the same mass. So that tells you a couple things when we translate this problem to a Newton's second law problem. We start talking about forces, which is that if we have one mass times one acceleration, it equals the same force no matter what. So both objects, because they have the same mass and because they have the same acceleration due to gravity in this case, you end up with that they experience the same force. And there is that one and only force. Okay? The other thing that you can consider is thinking about that horizontal versus vertical motion. We've got two objects, and this is where our whole definition of free fall began, if you think back to what we're learning, which is there's only acceleration in the vertical direction. Horizontally, there's no acceleration there. We used that over and over to solve free fall problems. You now know that where there's an acceleration observed on a mass, it means there's a force acting. So as we consider how does this really work, and you try to create a paragraph that defends your answer that these two free body diagrams are what they're supposed to be, there's only an acceleration in the vertical direction. And how big is that acceleration, or what causes it? Then you can come back to your free fall and the force of gravity.